The Xiaomi robotics team has introduced a foundational model trained on over 100,000 hours of real-world robot manipulation trajectories. This massive volume of data ingests into a single Vision Language Action, or VLA, foundation model. The sheer scale of this data injection results in a significant shift in the robot's physical capabilities. The system can be placed into an environment it has never encountered or mapped during its training. It receives a plain natural language instruction from a human operator. The robot executes the task immediately, out of the box, without any additional programming or localized training. Achieving this level of zero-shot adaptability challenges long-standing assumptions about the limits of robotic learning. These results suggest that the primary challenge in robotics is moving away from the design of individual algorithms and toward the acquisition of training data at scale. Historically, robotics has been limited by small datasets generated in highly controlled, lab-based settings. When models trained in these clean environments face real-world variables, like unpredictable lighting or novel objects, they typically fail. Xiaomi Robotics 1 presents the case that high-volume, real-world data is the most viable path to overcoming these generalization barriers. Building a dataset of 100,000 hours required a new approach to the physical data collection pipeline. The researchers used handheld devices known as the Universal Manipulation Interface, or UMI. Human operators use these UMI devices to quickly capture precise 3D spatial motion data in everyday, cluttered physical environments. This method avoids the slow pace and high cost associated with traditional robot-only teleoperation. Collecting clips in unconstrained settings introduces the physical chaos and variance the model needs to learn robust behavior. These recordings capture both the visual scene and the exact kinematic trajectory paths of the movement. These trajectory clips serve as the raw training material for the action generation model. By utilizing human-driven collection, the team reached a data volume that would be impossible to achieve through robot hardware alone. To make this massive dataset useful, the team developed an auto-labeling pipeline. Instead of static labels, it annotates specific state transitions occurring within a clip. Annotating this physical delta provides precise conditioning, linking the movement vector directly to the intended outcome. Because the model's actions are conditioned on physical state changes, the system demonstrates an understanding of physical cause and effect. The labeled trajectory data is processed using a two-stage training protocol. This involves a pre-training phase followed by a post-training alignment phase. During pre-training, the model ingests the full 100,000-hour corpus to develop a broad capability for generating actions. This phase gives the model a generalized understanding of how objects move and interact in the physical world. The second stage, post-training, focuses on alignment. Here, the broad action generation policy is mapped to the mechanical constraints of a specific robot embodiment. Post-training also aligns the model with the imperative natural language instructions that humans use to prompt robots in the real world. The model shows high efficiency during this fine-tuning stage, adapting to complex, dexterous tasks with very little new data. This two-stage approach effectively builds a physics engine in the first stage and teaches it how to pilot a specific body in the second. The efficacy of this architecture is confirmed by results across several simulation benchmarks, including RoboCasa 365. The previous state-of-the-art success rate for this benchmark was 46.6%. Xiaomi Robotics 1 reaches a success rate of 57.6%. An 11% absolute improvement in this benchmark is a significant departure from the incremental gains typical of previous models. In the RoboDojo benchmark, the prior state-of-the-art score was 13.07. Xiaomi Robotics 1 achieves an average score of 20.07. These benchmark wins are a direct result of the two-stage training protocol and the scale of the 100,000-hour dataset. These impressive final numbers indicate that sheer data engineering at massive scale consistently outperforms isolated, small-scale algorithmic refinement. Perhaps the most significant finding is that Xiaomi Robotics 1 exhibits predictable scaling behavior based on model size and data volume. This draws an explicit structural parallel between the scaling laws of large language models and the trajectory data used in robotics. The scale achieved during pre-training transfers directly to real-world performance, establishing a clear equivalency between trajectory data and linguistic tokens. This research suggests that robotics is beginning to see the same predictable scaling benefits that revolutionize natural language processing. This finding challenges the industry's historical focus on engineering specialized architectures for every individual task. The primary constraint now shifts to the physical infrastructure and hardware required to harvest and label real-world motion at this scale. Success in this field will likely depend on which entities can maintain the most efficient data harvesting operations. The experiment indicates that generalization is no longer a fixed barrier, but a function of the volume of training data. The performance of physical manipulation is increasingly defined by the total hours of real-world training experience. This is Cynthia Collabs, translating research into reality.